Have you ever looked at something and thought, is that a real pattern or is it just a weird coincidence? We do it all the time, but how do we actually know for sure? Well, it turns out there's a fantastic statistical tool designed to do exactly that, to separate a real trend from just random noise.
You know that feeling, right? You crack open a bag of candy, or maybe you're looking at some survey results, and something just feels off. That little gap between what you thought you'd see and what's actually right in front of you, that feeling is the starting point for some of the most important ideas in statistics. Let's stick with the M&Ms. So Mars, the company, actually publishes the official color percentages they're aiming for. But when one group went and counted 506 real-world candies, the numbers didn't quite match up. So the big question is, was their bag just a statistical fluke, or is something else going on with the official numbers? That's the kind of mystery we're going to solve today.
All right, here's our game plan. First, we'll break down the core ideas, what we actually see versus what we expect to see. Then we'll look at our first tool, the goodness of fit test, with a case study about market share. After that, we'll check out the test of independence to settle a debate about beer preferences. And finally, we'll wrap all up.
Okay, first up, observed versus expected data. This is really the heart of the whole thing. Every statistical test like this really boils down to a conflict between these two ideas.
So on one hand, you have your observed data. This is simple, right? It's what you actually go out and count. It's the real-world evidence you collect. And on the other hand, you have your expected data. This is your baseline, your theory. It's what the M&M's website says you should have. The whole point of our test is to measure the size of the gap between the two.
And the tool we use to measure that gap? It's called the chi-square test. But honestly, the best way to think about it is as a surprise score. That's it. If what you actually saw is super close to what you expected, you get a low surprise score. No big deal. But if your real-world numbers are way off from the theory, well, you're going to get a really high surprise score. So let's dive into our first method. It's called the goodness of fit test. And the name pretty much says it all. We use this to see how well our observed data, like our M&M's colors, fits with a known theory or an expected pattern.
Now, before I throw a scary-looking formula at you, let's just talk through the logic, because it's actually pretty simple. For each of your categories, like each M&M's color, you just do 4 quick things. 1, you find the difference between what you saw and what you expected. 2, you square it, just to make sure the number is positive. 3, and this is the key part, you divide that by the expected number. This kind of puts everything on the same scale. Finally, you just add up all those little results for every color, and that gives you your total surprise score.
And there it is. See? Not so bad when you know what it's doing. All this formula is just a formal mathematical way of doing exactly what we just described. It's the official recipe for our surprise score.
Okay, theory is great, but let's see this thing in action. We've got a case study from a firm called Scott Marketing Research. They wanted to know if a competitor's new and improved product had actually managed to steal away customers and change the market share landscape. So here's the data. Based on how the market used to be, they expected to see the numbers in that middle expected column. But when they surveyed 200 actual shoppers, they got the numbers on the right. You can see Company A seems to have lost some ground, and Company C, the one with the new product, gained some. But the question is this a real shift, or is it just random noise from this one survey?
So they ran the numbers. And what's really cool here is that you can see exactly where the surprise came from. Look at Company B. It was super close to what was expected, so it barely adds anything to the total score. But companies A and C, they were pretty far off, and they're the ones really driving up that total surprise score.
And after adding up the scores from all 3 companies, the final chi-square value, our total surprise score, is 7.34.
Okay, so what does a score of 7.34 actually tell us? Well, in statistics, you compare your score to a critical value. Think of it like a line in the sand that you agree on beforehand. If your score crosses that line, you can be pretty confident that your result isn't just a fluke. And in this case, 7.34 was way over the line. So the verdict? Yeah, that new product really did shake up the market.
All right, that's great if you have a pre-existing theory to test against. But what if you don't? What if you're just curious if 2 different things are somehow connected? For that, we need our second tool, the chi-square test of independence.
And for this, let's look at a case study from Alber's Brewery. They make a light, a regular, and a dark beer. And they wanted to answer a classic marketing question. Do men and women prefer different types of our beers? Or are gender and beer choice totally unrelated or, independent of each other?
So they went out and surveyed 150 drinkers, and this table shows the raw numbers of what they saw. 20 males like the light beer, 30 females like the light beer, and so on. Just glancing at it, it kind of looks like there might be some differences. But again, are these real patterns or just random chance in this particular group of 150 people?
So we do the same calculation, but here's the clever twist. To get our expected numbers this time, we calculate what the world would look like if there was zero connection at all between gender and beer choice. Then we use our chi-square test to measure the gap between that totally independent hypothetical world and the real world they actually observed.
And after running all the numbers, the final surprise score for the brewery data comes out to 6.12.
So, is 6.12 a big surprise? Yep. Just like before, it's high enough to cross that statistical line in the sand. This score is way too high to be a random fluke. So, the verdict is in. Beer preference is not independent of gender. Based on this data, there really is a connection there.
So we've looked at two really powerful ways of using the same core idea. Let's do a quick recap just to make sure the difference between them is totally clear.
The goodness of fit test is what you use when you have one variable, like candy color, and you want to compare it to a known model. You're asking, does my data fit the theory? The test of independence is for when you have two variables, like gender and beer preference, and you want to see if they're connected. You're asking, are these two things related?
So, at the end of the day, here are the big things to remember. The chi-square test is your go-to tool for telling the difference between a real pattern and random noise. It all comes down to calculating that surprise score. A high score is a big deal. It means your data is screaming that your initial theory was probably wrong. A low score? It means everything looks pretty much how you expected. No surprise there.
But really, the chi-square test isn't just some boring formula. It's a whole new way of looking at the world and thinking critically about the patterns you see every single day. So now that you've got the tool, what's the first thing in your world you're ready to put to the test?